Part 2 of this video series will describe the results associated with the algal biofuel example. A facility of this size is capable of producing approximately 65,500 metric tons of algal oil per year from 5,430 hectares of pond surface area. Based on the assumptions in this model, the total capital investment for this facility is roughly $315 million. This total does not include any cost associated with procurement of the land itself. Furthermore, the estimated annual operating cost is $116 million, which results in a unit production cost of $1.77 per kilogram of algal oil and a net unit production cost of $1.56 per kilogram of oil. The net unit production cost takes into account the additional savings associated with the utility integration described in Part 1 of this video series and the sale of the protein for animal feed. The results calculated for the return on investment, payback time, etc. are based on selling prices of $1.80 per kilogram of algal oil and $181 per metric ton of the protein for animal feed byproduct. Based on these values and the associated production rates of algal oil and protein byproduct, the return on investment, or ROI, for this project is calculated to be 13%, which indicates this may be a promising investment depending on the validity of various assumptions. The Economic Evaluation Report also provides a summary of the magnitude of each component of the annual operating cost as shown here. In this example, the facility-dependent cost is the greatest contributor to the annual operating cost, followed by raw materials and utilities. The facility-dependent cost is calculated based on estimates of annual maintenance, depreciation, and miscellaneous costs. The financial results from SuperPro are calculated based upon a set of default values and user specifications entered into the model. The parameters which impact the financial results can be classified into the following categories. 1. Information associated with individual operations and streams. This includes the unit costs and quantities of each raw material, the disposal costs and amounts of relevant waste products, the unit costs and hourly requirements for various labor types, the unit costs and amounts of various utilities, etc. The selling prices and quantities of the products are also taken into account for certain calculations. 2. Equipment-related information. This determines the capital and operating costs associated with each equipment unit. 3. Section-related information. This includes cost factors that are used to determine the capital and operating costs for each section of the process. And 4. Process-related information. This includes economic evaluation parameters that are specified at the process level, such as time valuation, financing, production level, and operating cost information for the entire project. Each of these cost categories will now be described in greater detail. Resource requirements associated with materials are determined based on the mass and composition specifications for each of the flowsheet's input streams. To determine material costs, the annual flow rates of each raw material are calculated by SuperPro and multiplied by the unit costs specified on the Economics tab of each material. The material costs for this example are shown within the Economic Evaluation Report. Other costs and revenues associated with streams are determined based upon specifications in the Stream Classification dialog. From this dialog, you may specify selling prices for output streams classified as revenue or credit. You may also specify treatment or disposal costs for output streams classified as waste. Furthermore, for an input stream classified as a raw material, a purchasing price is automatically calculated by SuperPro based on the stream's composition and the purchasing prices of its ingredients. In addition, in the lower right corner of this dialog, a main product or revenue stream and its flow basis can be chosen from the list of input and output streams that have been classified as revenue streams within this project. Annual revenues for the process are then calculated based on the unit prices and quantities of all revenue streams associated with the process. These revenues are reported in the economic reports using the main product or revenue rate as the reference mass flow rate. So in this example, the total revenue is reported per kilogram of material in the algal oil stream. Typically, a production process is designed to manufacture a main product that will be the revenue source, although in some cases other side products provide substantial supplementary revenues. For processes which produce multiple products, you may designate only one of the revenue streams as the main product or revenue stream. However, all revenue streams will be incorporated into the revenue calculations for the process. For instance, the revenues associated with the protein-rich animal feed byproduct are included in the revenue calculations within the economic reports for this example. Also note that the monetary benefits for the processing of influent streams, for example, credits for processing waste CO2 that was generated by another facility, and the sale of generated electricity may be included in revenue calculations. In this case, there are savings associated with the on-site production of electricity as well as utility reduction due to the heat integration described previously. Specifications for utilities and other resources such as labor are defined at the operation level. For instance, the utility requirement for the degumming heater is calculated by SuperPro based upon the calculated inlet stream temperature, the outlet stream temperature, the stream's heat capacity, etc. Labor requirements and auxiliary utility requirements could also be specified on the Labor etc. tab for this operation. The total requirement for each resource in each operation in the flowsheet is then multiplied by its respective unit cost to compute the associated operating costs. For instance, the labor costs associated with this example are shown here. In addition to costs related to streams and operations, there are various costs associated with the process equipment. For instance, the purchase cost of equipment affects the direct fixed capital investment of a project, and it indirectly affects the annual operating cost. SuperPro is equipped with correlations for estimating the purchase cost of equipment based on its type and size. However, the built-in correlations for most types of equipment are more suitable for fine chemical and pharmaceutical types of facilities than for large-scale algae production and processing. For these types of processes, we advise users to enter their own equipment cost data for better accuracy. User-defined costs may either be specified as a specific value or as a user-defined cost model. In this example, a user-defined cost model has been chosen for the purchase cost estimate. The user-defined cost model allows a user to provide a cost versus size correlation that will be used by the application to estimate the cost of a piece of equipment in the form of the power law equation shown here. In this equation, C0 is a reference cost, Q0 is a reference size, and A is an exponent, usually less than 1. The user must also provide a range of size values where a given cost correlation is valid. In this example, the specifications ensure that for all tanks up to a maximum volume of 4,000 cubic meters, the capital cost will be $800,000 times the quantity, tank volume divided by 3,600, taken to the 0.7 power. Note that this value is also adjusted for inflation based on the year of analysis and the inflation rate specified at the project level in the Economic Evaluation Parameters dialog. Also note that it is possible to store the user-defined cost model information associated with each of your equipment types in the user database for future reuse. Detailed information on how to do this is provided in the README file of the lysine example that ships with SuperPro Designer. After the base purchase cost for the equipment is estimated, there are several adjustment parameters that are applied to it. These parameters affect the total purchase cost of the equipment, the direct fixed capital, the facility operating cost, and other economic results. Furthermore, any costs associated with consumables, i.e., items that are used by the equipment unit for one or more batches before being disposed, can be specified on the Consumables tab. Using the cost models for each equipment unit and their respective cost adjustments, the total equipment cost may be calculated based upon the quantity of each equipment item that is required. Notice that roughly 80% of the total equipment cost in this example is associated with the raceway ponds due to the very large number of ponds required. Once the equipment costs are determined, SuperPro Designer can calculate the total direct fixed capital, or DFC. The DFC contributions are estimated for each individual section of a process. By default, each section's DFC is calculated as the sum of direct, indirect, and miscellaneous costs associated with that section's capital investment. The direct costs include elements that are directly related to an investment, such as the cost of equipment, process piping, instrumentation, buildings, facilities, etc. The indirect costs include elements that are indirectly related to an investment, such as the costs of engineering and construction. Additional costs, such as the contractor's fee and contingencies, are included in miscellaneous costs. Note that the default process section specific cost factors for piping, instrumentation, buildings, etc. are more appropriate for high-value chemical and biochemical plants. Therefore, those default values will greatly overestimate the total capital cost associated with an algae production facility. As a result, the section-specific cost factors for piping, instrumentation, insulation, buildings, engineering costs, etc. have been zeroed out in the capital cost adjustment dialog boxes for each section of this process. Instead of using those factors to calculate the total DFC of the facility in this example, the section DFCs for this process are each based on equipment purchase costs and higher than normal equipment installation cost factors. These installation cost factors are assigned to each individual equipment unit through the Adjustments tab of each of their equipment data dialogues. For instance, the installation cost factor for centrifuge DC102 is shown here. In this case, the installation cost associated with the centrifuge is set to be equal to 2 times its purchase cost. Therefore, the total DFC associated with this centrifuge is 3 times its purchase cost. For certain other units in this process, the installation cost factor is much lower because there is less supporting infrastructure required. For instance, the installation factor for the raceway ponds is only 0.2. Because the installation cost factors assigned to each equipment item in this model are intended to account for their associated piping, instrumentation, insulation, buildings, engineering costs, etc., there is no need to include other cost multipliers in the capital investment dialog shown previously. In addition to the section-level capital cost specifications, there are also specifications at the section level related to operating costs. Here, you can specify how various operating costs should be calculated for each section. For instance, The specifications that are used to calculate the facility-related annual operating costs are shown on the first tab. Like the capital cost adjustments dialog, the operating cost adjustments dialog provides a variety of ways to have costs calculated for various aspects of the process. In this case, the facility-related operating costs are calculated based on maintenance, depreciation, and miscellaneous costs. Other tabs of this dialog provide options for calculating the annual costs related to labor, lab QC/QA expenses, utilities, and miscellaneous expenses such as ongoing R&D, process validation, etc. The remaining specifications related to process costing are performed at the project level. To view or modify the project-level cost parameters, simply right-click on an empty area of the flowsheet and then select Economic Evaluation Parameters. Here you can specify parameters such as the year of analysis, construction period, inflation rate, etc. On the other tabs of this dialog, you can specify information related to financing of the project and depreciation, production rate and product failure rate, and expenses related to taxes, sales and marketing, and royalties. Based on the capital and operating cost specifications, SuperPro determines the total fixed capital estimate, annual operating cost, profitability, including margin, return on investment, and payback time, cash flow calculation results, etc. Various economic results may then be viewed from the Executive Summary, the Economic Evaluation Report, the Cash Flow Analysis Report, and the Itemized Cost Report. The tables shown previously in this video were all included in the Economic Evaluation Report. If you are planning to perform capital and operating cost estimations for multiple similar projects, keep in mind that most of the multipliers used for the cost analysis can be stored in SuperPro's user database and retrieved for future work on those projects. This facilitates standardization between projects and improves the accuracy of cost estimation. For information on how to take advantage of the database capabilities of SuperPro, please consult the SynFarmDB document in the Examples SynFarm subdirectory of the SuperPro installation. According to the U.S. Energy Information Administration, 134.5 billion gallons of gasoline were consumed in the United States in 2013. In addition, the annual usage of jet fuel in the United States was 20.2 billion gallons in 2009, and U.S. diesel consumption was approximately 50 billion gallons per year in the mid-2000s. Based on these numbers, the densities of each fuel, assumed conversion rates from tag to various end products, and the aerial productivity calculated from this model, the total land mass required to replace all U.S. fossil fuel consumption with algae-derived fuel may be calculated. These results are shown in the table here. As this table demonstrates, current U.S. transportation fuel demands could be met through conversion of algae products into fuel. However, doing so would require extremely large facilities. Furthermore, based on the assumptions within this model, replacing current production of these three fuel types would require roughly 10.7% of the entire continental United States landmass. However, research into methods of maximizing algae production are ongoing, and the estimates for future algae productivity vary tremendously from one source to another. For instance, the U.S. Department of Energy estimates that it may be possible to produce enough fuel from algae to replace all petroleum fuel in the United States by using only 0.42% of the U.S. landmass, assuming substantial gains in algae productivity in the future. This is less than 15% of the area currently devoted to corn production in the United States. This concludes the Algal biofuel example video. For additional details on how to create models in SuperPro, and for information on additional capabilities of SuperPro, please refer to the SuperPro manual and the other SuperPro example files, all of which are included with both the free SuperPro evaluation version and the full SuperPro application. Please also refer to the other online training videos located here. Thank you.